Hello, this is Philip Myers of PEMY Consulting. We hear a lot about big data, artificial intelligence, and data science these days. But does this stuff really apply to the smokestack industries and to tank engineering? While billions of mouse clicks per minute pervade the internet, the data for engineering of facilities is by comparison sparse, expensive, and hard to come by. Underlying all these disciplines is statistics and probability. So is data analysis possible and effective for general engineering problems? I have some cases to show you that will help you decide. This tank has an outer perimeter that is settling faster than the interior indicated by the blue region. Here's a side view showing the bottom and the sides. The worst radial shown by the blue line is plotted on the right for a numerical finite element analysis study to determine if the stresses are excessive. You can see the open circle points indicating the actual measured settlement at the worst location, measuring the included noise. Filtering out noise is important because these points are not what is actually going on, and using these points would result in very high stresses falsely indicating failure. But taking the noise out is a balance between locally applied statistical smoothers and actual deformations, which is where data, experience, and stats all come together. In another settlement example, it is now relatively common to use laser scanning data, which instead of 8 or 16 points has thousands or millions of points. The example here shows a plot of laser scan data. The key point is knowing how to manipulate and analyze the data, which gives better and more accurate results. Here we are trying to determine whether vendors of pressure vacuum valves are properly certifying flow rates in accordance with API 2000. A test was conducted where each vendor measured the airflow through the same orifice. The data was analyzed by what is called an analysis of variance, or ANOVA. The results are shown with the red 95% confidence bands. You can see that vendors A, B, C differ significantly from vendors D, E, F. This plot shows how vendor bias or systematic error in measurement determines and dominates the noise. Finally, we developed criteria based on inter-laboratory standards applied to assays to show how and why a gold standard is needed to set up acceptance criteria. Imagine you were a surveyor hiking around in this hilly scene to measure the heights of various hills, and you also want to find the very tallest hill. This appears to be a straightforward task, but then a fog rolls in and visibility is shot. To find the peak, you have to rely on the gradient or slope of the ground. At each step, if you move up, then you are more likely to find the peak. You can even reach the peak using this algorithm, but this won't find the highest peak. This is essentially the problem of optimization and the branch of statistics called design of experiments, or DOE. Rotating a steel stud with pressure against a steel plate is a quick way to attach studs to tanks and vessels. However, the opposite side gets hot as well, and if this is done in equipment with flammable vapors, the question becomes, is the time and temperature sufficiently far away from the required minimum ignition energy to create an explosion in the presence of flammable vapors? Like the hill measurement problem, we want to find the boundary between ignitability and non-ignitability over the landscape of variables that have many hills. We even used an adaptive algorithm that reduces the number of trials to find the hazard boundary for this problem. Here's another DOE problem where the goal is to optimize the number, sizes, propeller types, horsepower, shear energy per unit volume, flow patterns, and other variables to minimize sludge buildup in crude oil tanks. Earl Crochet and I co-chair API 656, meant to help tank owners and operators cope with the increasing natural disaster incidents impacting oil storage facilities. We have been able to apply extreme value stats to a wide variety of problems. In this plot, we have rainfall data since 1900 for Fort Collins, Colorado. Then we get this plot where we see that the distribution of extremes nicely follows a mathematical pattern. It turns out that this idea widely applies to almost all real data distributions and is therefore something we can take advantage of. Here's an example of an extreme value validation study we did on the Iowa River Basin, where the site of interest was Honcher Auditorium, a performance venue for the University of Iowa in Iowa City. This facility was originally built in 1972, then flooded out in 1993 and 2008, and replaced in 2019 by a new auditorium designed by Cesar Paley. The new structure is 240 meters north-northeast and 3 meters higher in elevation. The question we need to answer is, what is the elevation at the site? What discharge rate will produce a flood that reaches this elevation? And what is the probability of exceeding that discharge rate? In API 656, we show how to use extreme value stats to create plots like this, which answer this question. Tank corrosion pitting rates are an area where extreme value statistics can more accurately determine equipment lifespans. This plot shows a typical tank bottom corrosion rate for a given company. In this plot, the use of data can be used to actually more accurately determine tank bottom life. We call this equivalent risk. The idea of similar service can also be applied if the grouping of tanks is done properly, where each color here represents the corrosion rate distribution at different facilities within a given company. The technical name for this is Directed Acyclical Graphical Network with Nodes and Edges. These graphs are used to represent probabilistic graphical models in Bayesian belief networks. Because of computational intensity, only in the last decade or so have computational algorithms become sophisticated enough to solve them. In our last example, these large USTs are located in a highly sensitive environment. The facility owner has proposed a system of systems, including precision mass measurement leak detection, soil vapor monitoring, inventory reconciliation, inspections, and so on. If one sensor shows a leak but the others do not, what action should be taken? We know that all sensor systems have false positives and negatives. Since a shutdown is extremely costly and disruptive, how do we fuse all the sensor readings into the best possible action based on all the evidence? In this case, PEMY proposed to the stakeholders that the best approach is to use evidence theory, more specifically Dempster Shafer theory, which is a generalization of Bayesian statistical theory. The theory is complex, so we won't go into it. However, we point out that everyday applications for the use of evidence theory exist that require the best tools that data analysis has to offer. I hope this has given you an appreciation of how the subject we all probably hated in school has not only revolutionized the world, but how it can even be useful in the world of not so glamorous mundane engineering problems. Thank you, and see you next time.